Hey guys, and welcome to this lesson all about the Pythagorean theorem. And perhaps you've been exposed to the Pythagorean theorem before, but I think it's something that's worth revisiting and a great opportunity to see how roots, and in particular square roots, can be really helpful. So let's take a look at our first right triangle here. It's a right triangle because, well, it has a right angle on it. And just some terminology, in a right triangle, the side opposite the right angle, the longest of the three sides of that right triangle, is called the hypotenuse. The other two sides of the right triangle are called the legs. So here we have a leg whose length is 4 centimeters, another leg whose length is 8 centimeters, and the side opposite the right angle, the hypotenuse, well, we don't know how long it is right now. And perhaps you know the relationship between the lengths of the sides of the legs and the hypotenuse of any right triangle. This is the Pythagorean theorem, and the Pythagorean theorem, says that if you take the square of the length of one leg and you add it to the square of the length of the other leg, that sum will equal the square of the length of the hypotenuse. Sometimes succinctly just stated as a squared plus b squared equals c squared, where a and b represent the lengths of the two legs, and c represents the length of the hypotenuse. All right, phenomenal. So here is the Pythagorean theorem, or the formula that it implies, and let's use that to find the length of this unknown hypotenuse, x in this case. So since we do have the lengths of two of our legs here, we can go ahead and substitute those in and say that 4 squared plus 8 squared, whatever that sum is, that has to be the square of the length of our hypotenuse. In this case, I might as well just write that as x squared because that's the variable we're using here. All right, so 4 squared is 16, 8 squared is 64, okay, equals x squared. Let's add 16 and 64, that's 80, equals x squared. So we are looking for a number that multiplies by itself to give 80. And I'll tell you right now, it's not going to be a nice integer, right? If this were 81, oh, that'd be nice, right? Then x would be 9, because 9 squared is 81. But what number squared is equal to 80? Well, by definition, the square root of 80 is the number such that if you multiply it by itself, if you square it, you get 80. So here's an example of how a square root can be really, really helpful here in the context of the Pythagorean theorem. Now, a quick note, there are two numbers that square to give 80. 80 has two different square roots. One of them is positive and one of them is negative. But since we were talking about a length right here, a negative number would not make any sense. So we would say that the length of our unknown hypotenuse in this case is exactly the square root of 80. And if I were to put a unit on it, I might say centimeters. So here's the Pythagorean theorem. We use it in this particular example, and we had to use the square root in order to find our unknown side length. All right, let's do another one. Note that in this right triangle right here, we do know one leg length and the length of the hypotenuse, but this is another leg that we don't know its length right now. So very similar to what we had before, we've got the Pythagorean theorem, the square of the length of one leg plus the square of the length of another leg is equal to the square of the length of the hypotenuse. So we do know one leg length, 4 inches, so 4 squared plus unknown x squared is equal to, well, the length of the hypotenuse, 6 inches squared. All right, let's do it. So we got 16 plus x squared equals 36, which means I'm thinking that x squared has to equal 20, right? I'm thinking that if 16 plus some number equals 36, well, that's some number that's got to be 20. I mean, like 16 plus 20 equals 36. So if this number squared is equal to 20, well, that number has to be the square root of 20, right? That is the number that multiplies by itself to give 20. By definition, the square root of 20. Now, are we always going to get weird square root answers? No. Are we going to get them often? Sure. And just it's really good to have that tool in our arsenal to deal with square roots. One more example. Holy cow. A lot of square roots all over the place. So once again, we do know the length of our hypotenuse. We do know the length of one of our legs. We do not know the length of our second leg. So again, it looks like a job for the Pythagorean theorem. All right, we do know the length of one of our legs. The square root of 11, squared plus unknown number x squared equals the square root of 15, that number squared, right? The square root of 15 was the length of our hypotenuse. Well, what is the square root of 11 squared? Well, by definition, if I have the square root of a number and I multiply by itself, I'll get that number, just 11. Oh, kind of cool, okay. 11 plus x squared equals, well, 15, or rather the square root of 15, multiplied by itself is 15. That's what it means to get the square root of 15. If you have the square root of 15, then if you multiply by yourself, you give 15. Oh, cool, check it out. So I've got 11 plus some unknown number equals 15. I'm thinking this unknown number, x squared, is going to be 4. Holy cow, what number multiplies by itself? What positive number multiplies by itself to give 4? 2. Check it out. So in this problem, where we happen to have all sorts of weird square roots all over the place, we ended up with a missing side length that was a very nice 2. So that was an introduction to the Pythagorean theorem and how we can use it and how we can use radicals and roots, particularly square roots, in the context of the Pythagorean theorem. So I hope you found this helpful, and I hope you enjoyed.